Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. Today we will cover lecture 7 will cover the relative motion analysis of using translating axis. So let me explain a little bit what do we mean by translating axis. What do we mean by translating axis? Translating axis means that we have a system by which this is an axis xy, and usually we measure something from this axis. So let's say this is a particle P and we have this position vector R underline. So this is usually fixed. Let's say I'm gonna fix this, so this is a fixed axis. What happens if the axis is moving? So let's say you are on a car or on a platform and you are moving or translating. So this one on your right, on your left is a fixed axis. This is a translating axis. Translating axis. So when we say a translating axis, we refer to the condition where the axis x and y are moving. Okay, so to start with, all the lessons that covered before are using fixed axis. So this fixed axis, as I told you, is where we fix the axis at a particular point. So usually x and y doesn't move, and we have the origin at O and it doesn't move. So these are fixed axes. Should be in terms of, should be plural rather than one. So there are cases where measurement is done on a moving translating axis, and we can determine the motion of the particle using the approach developed here. As I told you, if the axis is moving, let's say we are on a car and you are doing some measurement, so that is a translating axis. So xy is moving at a certain speed or velocity. So let's put that as a certain speed or certain. So this section only covers translating axis, but in the later on in the rigid body section, we will cover the rotational axis. Rotational axis is when you are not only translating, your x and y is not only moving, but also rotating at the speed of theta or theta dot, and it has its own angular acceleration. So that is, we will cover that later on, but in this section we will not cover that. We will cover much later on when we consider the rigid body. So fixed axis versus translational axis, that one we have covered before. So let's start with an example. So let's say we have a path. Let's say we have a path, and this is a path, and then we have a particle B. Particle B, let's say we have a particle B here, and we have a translating axis. So let's call that x dash and y dash. Okay, this is the translating axis, and we have a fixed axis, which is the fixed observer. So let's call that x and y. So this is a fixed one. Okay, and let's call the origin for the fixed axis as O, and the origin of the translating axis as A. So to start with, we will cover the position vector of B. So I'm drawing this vector, and I call this position vector B, R subscript B underline. Okay, and we have this, the position vector of the translating axis as position vector A. So it's position vector A. So R subscript A underline. And then finally, we have what we call as position vector B relative to A. Yeah. So this is position vector B, position vector R, B relative to A. Yeah. So position B relative to A is a bit special to us. So I'm going to highlight this a little bit by this yellow color. So from there, we can write the equation of the position by looking at this arrow vector. So position vector B, my R is not that beautiful, so position vector B, let's use a thicker line perhaps. So position vector B, this line, position vector B equals to OA plus AB. So we can say that it is equals to position vector A plus position vector B relative to A. So when we differentiate this equation, so VB, the velocity of B, is equivalent to the differentiation of the position vector B, and we will have velocity A plus velocity B relative to A. And finally, acceleration B equals to the differentiation of the velocity vector VB, and that will give us acceleration A plus acceleration B relative to A. So it's a very straightforward thing, and let us mark this border by the red color. So this is the acceleration equation, this is the velocity equation, and this is position vector equation. So we have covered position vector, velocity vector, and the acceleration vector. So it's just a very straightforward application. So this example shows a train traveling 60 km/h. This is the train. So you got a train here going 60 km/h to the right, and you got a car going at a 45 degrees and at 45 km/h. So I've got to put there 45 degrees. This is 45 degrees, and the speed is given at 45 km/h. So we'll just have to put the data here. So we have the fixed axis, y over x here. So I'm now going to first, I usually do this labeling of the axis. So this is my origin of the fixed axis O, and origin of the translating axis A, and this is my train T. So this is T. Yeah, so point T is a train, and A is the point of the car. So from there, I'll draw the position vector. This is the position vector. Or what is this position vector? This is position vector of the train. So I'm going to put RT. And I also have this position vector here. This position vector is RA. And I have got the final position vector here, which is, I call that position vector train relative to A or relative to the car. So I can now write the position vector train RT, position vector train, equals to position vector A plus position vector train relative to A. So from here you can get the velocity of the train equals to velocity of A plus velocity of train relative to A. A is a car, yeah? So because we just want to find the relative velocity of the train relative to the car. So this is the vector equation that we want to solve. Before that, what are the data that we have? We've got the velocity of the train. So the train is traveling 60 km/h to the right. So we've got V train equals to 60 km/h. What is the direction? Direction is to the right in terms of, so the direction is, you look at this, is to the right, x, positive x. So we will use the unit vector I. So 60 kilometer per hour. So what is the velocity of the car relative to the train? So we've got that car motion, VA. So we know that VA is equals to 45 kilometer per hour, but at an angle, so it becomes cos 45 degrees I plus sine 45 degrees J. So it has the I and J component, right? So so from there we can write the equation of motion. So Vt relative to A, so Vt is 60 kilometer. So Vt is 60 kilometer per hour sorry. So it's 60 kilometer per hour I equals to VA 45 cos 45 degree I plus 45. I'm gonna erase this, yeah, because I'm gonna use a space. 45 sine 45 degrees J. And then we have Vt relative to A. So our Vt relative to A is V of the train relative to A can be defined as 60 minus 45. Cos 45 is 1 over sec 2 I, yeah, and then minus 45 1 over sec 2 J, and the unit is kilometer per hour. So that is the vector for the velocity of the train relative to the car. So can you find the acceleration of the train? Do we need to find the acceleration of the train? No, we don't have to find the. So that will be the answer for this question. So next one. So this is an example from where we have a plane A is flying to the north in a straight line at speed of 700 km per hour and also increasing at 500 km per hour square. And then plane B is moving also at the point 600 km per hour and reducing speed 100 km per hour square. This is a square, yeah. And then the radius of curvature for the path of B is 400 km. So the question is asking determine the velocity and acceleration of B measured from A. So what this question wants is VB relative to A, and also acceleration of B relative to A. So the simple thing to do is to first construct the XY axis. So I'll draw the XY axis, the fixed axis. So this is my fixed axis. So let me draw this and let me remove my face from this. So this is my XY axis and this is my O. O is the origin of the fixed axis. And who is translating? Translating is A. A is translating. So this is my translating axis. So X dash, Y dash. And what is the origin of this? Is A. In our literature, it is in A. So I'll draw the position vector of, this is position vector of A. And this is position vector of B. And this is position vector of B relative to A. So we wanted to find B relative to A. So the velocity of B. So position vector B is equivalent to position vector of A plus position vector of B relative to A. Yeah. So from there you get the velocity equation. VB equals to VA, velocity of A plus, so ugly. So let me correct this. VB equals to VA plus velocity of B relative to A, and subsequently I can write the same for the equation acceleration of B equals acceleration of A plus acceleration of B relative to A. I usually find it helpful for me to draw the diagram before I can write the equation for the position vector and also for the velocity. So I've got this all three blocks. So now I'm going to use, so what is the velocity of A? The velocity of A, I know that A is 700 km to the north, so in the y direction, so VA is 700 J, kilometer per hour. Not going to write the units. So VB is also tangential to that is 600 km per hour, 600 J. What is the, then we can write VB equals to VA plus VB relative to A. So we can find that the velocity of B measured from A is VB minus VA from this equation here. So it is VB 600 J minus 700 J. So it's equals to minus 100 J kilometer per hour. So that is the answer for the first question. That VB is minus 100 km per hour. VB relative to A. So B, when measured from A, as though B is moving to in the negative direction of A, because A is passing B. It's just a way of representing the equation. So we have the answers for B relative to A. What about the second one? Acceleration of B as measured from A. So we got the acceleration of A. What is the acceleration of A? The acceleration of A, we know that A is 500 kilometers per hour. So A is 500 J is in kilometer per hour square. I'm not going to write the unit here, but be reminded of that. So I'm going to remove this unit here. So it's 500 J in the positive J section. So what about B? B has got two components, yeah, because we have learned from curvature. So it has a tangential component. So B has two components, yeah. So I'm going to put here AB equals to ABN normal and AB tangent. Yeah, what we have is the tangential component. What is the tangential component? We know from here that the tangential component is 100 kilometers per hour square. So that is equals to 100 kilometer in the minus J direction. It is going in the negative Y direction, so it's a minus 100 J kilometer per hour square. Yeah, so I'm going to block that. So tangent data, we've got that. What about N here? So we know that ABN equals to ABN, the normal component. I have to rub this data up here. So I'm going to remove this data here with some space to write. So let me go here, yeah. So the acceleration of B in the N direction, change the color again, equals to V square over rho. And the direction is always to the negative X direction, in the direction of the curvature. So that one, the V square is 600 km per hour square divided by rho. You don't have, because rho is in kilometers, so it's 400. Yeah, So you have got that answer. 600 divided by 400 square. So we will have AN as 900. 900 900I. 900I kilometer per hour square. That is the unit, yeah. So now we can write the whole equation of AB. So we know what AA is and we know what AB is. So the equation for, look at the equation of acceleration here. So AB, let's write AB. So AB equals to minus AB relative to A. So AB equals to 900I. AB, so let me 900I from here, yeah, from this 900I minus 100J equals to AA. AA is 500J. I'm looking at this equation, guys. I'm using this equation and I'm finding the value of AB here. Where do I get the value of B? Here, AB, ABN plus ABT, and the value of AA. Excuse me. So then we have the acceleration of B relative to A. Yeah? So we can get the answer. The acceleration of B when measured from A is equals to 900I. This one, this value goes to the right. So we will have 900I minus 600J. B relative to A. B minus 50J. 50, oh, 500. Okay, 900I minus 600J. Yeah. J. So there is a unit kilometer per hour square. So that's example 7.2, which give you the answer for this question that asks you the acceleration of B relative to A. Okay, so the next one. Okay, so this is example 7.3. Because of there's some technical problem with this example, I'll cover this example in the tutorial. Yeah, so I'll just put a note here. We'll cover this in tutorial 2. Okay, so that's the end of the lecture for this on the translational axis. Thank you very much.